So for those who didn't attend the last atom seminar, I'm going to introduce Professor Richard Elliott again. So he's a professor emeritus at the University of Akron in Ohio, USA. He currently teaches several courses on thermodynamics for undergraduates and graduates in chemical engineering. He's a co-author of the well-known books Introductory Chemical Engineering Thermodynamics for chemical engineering courses, and The Properties of Gases and Liquids, a reference book for chemical process design engineers. He has several research interests, from which I would highlight molecular simulations and perturbation theory for equation of state. And he's going to present something that he prepared for you guys from the thermodynamics course. Let's go.
Okay.
I'll stop my share.
I was wondering if I could ask a technology question. Sometimes I like to ask the class a question just to see if I can gauge, if I understand how much they understand, so that I can either go faster or slower depending on how how they respond. And so can we do that inside of Zoom? Can I say, here's a multiple choice question, how many students choose A? How many
we have done this using the Google Forms.
Oh, Google Forms.
Yeah, so we have, in other occasions, we created Google Forms and shared the link in the Zoom chat, but it's not a tool integrated to Zoom, it's an external tool. So
actually, Zoom has a tool.
I don't know if it's worth to do it on the fly, but that's how we did it. Thiago, you want to add something?
Yes, actually, Zoom has a tool for this type of questions. We actually don't know how to use it, but well, I think Yuri's idea is better. We can use a Google Forms if you want.
Yeah, could we create a question? I mean, I'll just be lecturing for a while before I get to a question like that. If we could just create a generic question where it doesn't even list the question, it just says A, B, C, D, and then we can read who wrote A, who wrote B, who wrote C, who wrote D, or not who wrote, but how many people wrote A,
okay.
How many people wrote. Yeah, I don't need to know who. I don't want to know who. People can be, shy, and I just want them to answer.
Right. So Thiago, you could create a draft with no question, no answer, just A, B, C, D.
Yeah. And
okay.
When Richard asks the question and says the answers, you can share the link in the chat.
Okay. And we can, okay. I'll do it right now.
Okay, great. I'll start working on the lecture then. Oh, I got to do a screen share first. Let's see if I can do that right. Can you see my screen now?
Yes.
Okay, great. I'll go to full screen mode. We'll see if how well that holds up. So good morning, everybody. It's nice to meet you, and I hope we'll get to know each other better over the course of this lecture, and maybe more lectures if you want some. The topic I thought I would pick up with today might seem like a strange place to start, with chapter 11, which is about activity models. But we're able to hit on a number of topics this way that I think are interesting and give you some insight into at least what I think are the interesting parts about chemical engineering. The idea that we can understand some things about chemicals and the ways that they interact, we can use that knowledge to quickly estimate the sizes and costs of chemical engineering equipment and processes in general. And with that insight and the ability to trade economics versus idealities, and then we can come up with the best economic answer to a lot of different problems. That for me is the beauty of chemical engineering. So I think we're getting some noise in the background. Somebody could mute their button. Okay, that sounds better. I think you've all heard of Raoult's law. Oh, there it goes again. And so the key that I'd like to talk about today is what I call modified Raoult's law. So all we're doing is we're recognizing that Raoult's law is a little bit too simple. And so we're going to add a fudge factor, a correction factor, to make it work better. And that fudge factor is called the activity coefficient. And we can come up with various activity models. And the only ones that I'm going to talk about today are the Margulies model that I call Margulies one parameter model. There's a 2-parameter version, but I'm only going to talk about the 1-parameter version today. And one of the keys then is to characterize the parameters of the activity model. So when we say that the solution is not ideal, that's essentially what modified Raoult's law is correcting for. Raoult's law is for ideal solutions, modified is for non-ideal. Well, the first question then is, how non-ideal is it? Well, the parameter enables us to specify how non-ideal it is. And then I want to introduce a very simple adaptation of this Margulies 1-parameter model that gives us the ability to estimate how non-ideal it is based on essentially hydrogen bonding. And I think everybody's heard about hydrogen bonding since high school in a biology class. And so as chemical engineers, we should definitely know something about hydrogen bonding if you already knew about it in high school. So let's use that insight that we heard about for so long to help us make some estimates of how to design our solutions, our formulations. It could be product formulations. The same concepts could apply to designing makeup or soap or many, many other types of chemicals. Once we've got the concepts, we can adapt to many product designs and process designs. So those are the topics that I want to hit today. Hopefully you've heard of Bloom's taxonomy before, but if you haven't, let me just outline it quickly. It's a way of organizing learning so that you recognize that there are various ways of learning, from just the basic remembering level, but there's a key to that that's got to do with long-term memory, right? So a lot of times students will cram for the test, and then as soon as that test is over, they go, oh gosh, I'm glad that's over with. I'll never think about that again. Well, that's not really learning, right? So learning means that it's put into long-term memory. And within this Bloom's taxonomy, there's a whole implication there, broader implication of we're really interested in learning as a science and how the brain acquires knowledge and stores it and then is able to recall it. And so all of this goes together. And so the beginning is putting something into long-term memory. That's actually a chemical reaction. And it takes about 48 hours to formulate a long-term memory. You have to want to learn the information, and then you have to encounter the information over and over again for about 48 hours before your brain decides, oh, you know what? I keep seeing this information, and I better put it in the long-term memory because I don't want to keep having to go and relook it up all the time. It's just wasting my time. So those are some of the keys to long-term memory. At the next highest level, you want to understand the problem statements and the meanings of the terms, and so we'll go through some of that. Then you want to be able to apply procedures, and the procedures that we'll talk about today are bubble point, dew point, flash, liquid-liquid equilibria, vapor-liquid-liquid equilibria. I won't get to solid-liquid equilibria. And for the most part, we're going to do that in the context of phase diagrams. We'll start where I give you a phase diagram and you just interpret it, and that's where we'll try to have some fun with some ABCD questions. And then the next phase is, as graduate students, well, as any engineer really, you should be able to compute your own phase diagrams. So let's do a little bit of that. And the two models that I'm going to use are this Margulies 1 model that I talked about, and the simple acid-base model for the Margulies equation, which we call the MAB equation, Margulies acid-base model. To get some orientation as to why we might care about any of these things, I think it's useful to take a look at how distillation works. Distillation is a very important process in chemical engineering. If you think about a reactor, let's just say A plus B goes to C plus D is your most elementary chemical reaction, right? Well, as soon as you do that, now you've got 4, because no reaction goes to 100% completion. Now you've got 4 components in a mixture, and they're no use in that mixture. You have to purify those to be able to sell them. So now you have one distillation column where you split, let's say, A and C go up, B and D go down in that first distillation column. But now A and B were the reactants, right? So you want to recover those reactants and recycle those so that you don't create a waste problem and you save some money. And so now you're going to recycle the A and the B, but you've got to split them from, you got to split the A from the C and the B from the D. So now you need 2 more distillation columns to separate those out. So for every 1 reactor, you need 3 distillation columns. And if you look at the economics of a chemical process, you'll see that about, let's give 10% for other operations, but about 70% of the cost of the process is distillation, with some of the heat exchangers and various things that you need to run a distillation column. And another maybe 20% is the reactor, and then you got 10%, 15% for doing other things. So 70% of every process is distillation. And so this is a really important process. We need to know how this works. And that's going to dominate all your economics. So let's take a look at how distillation works. The basic idea is to look at this. This is our first phase diagram, really. And this is a plot then of the temperature as a function of the composition, mole fraction of methanol. What we see is, well, let's take a look at this phase diagram and let's review. See, because we're going to have some questions about this, some A, B, C, D type questions. When the mole fraction of methanol is 1, that means we're at this temperature where the methanol is saturated. Now, there's another common name for that that temperature, and I wonder if you should think about, just for a second, you should know what that is without my having to tell you. If we look across on this axis, we can see what that temperature is for methanol, what the numerical value is. And I wonder if you could just tell me what you think that name, the common name for that temperature is. Just think for a second. We won't do the ABCD yet. Did you come up with normal boiling temperature or normal boiling point? Because that's what that is. Now, how do we know that it's the normal boiling point? Well, if the composition of methanol is 0, then what's the composition of water? It's just a binary system. So if there's no methanol, it must be 100% water. And since we know that water boils at 100 degrees C, we know that's the normal boiling temperature of water, then we must be at 1 atmosphere. And if we're at 1 atmosphere, that's the normal boiling temperature in general. And so this must be the normal boiling temperature of methanol. You see how that works? So this is sort of my perspective on how I want to approach the exchange of information here. I want you to think first, and you come up with the answers before I just spit them out. I think you'll get more quickly oriented that way. So I've labeled this phase diagram very carefully, and you can see that instead of just omitting this label or whatever, I've put this is the saturation temperature for methanol. I've indicated that very clearly because I've seen a number of situations where students will write that this is the temperature, saturation temperature of water. That would be wrong. When you're at 100% methanol, this must be the saturation temperature for the methanol. So there's just some sort of orientation to just look at this as methanol, see that this is an axis for methanol, and then say, okay, well, we must be starting from methanol. No, we're starting from 0 methanol. So you got to think that through every time you look at one of these phase diagrams. Another thing you should not forget to label, because I've seen people mix this up, is the vapor and the liquid side. So what we see here, how do we decide if this is vapor, and this is liquid, or this is liquid and this is vapor? Do we just flip a coin? How would you decide? Think about it. You need some sort of procedure for evaluating it, some way of thinking it through. And a lot of times the way that I find useful to think these things through is to take some extreme set of conditions. And if I can go to that extreme and figure out what it is, then I can sort of systematically back away and figure out what it must be under the more realistic conditions. So let's think about an extreme where we take the temperature to 1,000,000 kelvins or something. That's pretty extreme, so we can call that extreme. So do you think it's going to be vapor or liquid at 1,000,000 kelvins? I think it's going to be, everything's going to be a vapor. All right, so we know that way at very, very high temperatures, we've got a vapor. So if there's only 2 possibilities, this must be the vapor side. And every time I want to construct a phase diagram, I go through that process. I don't try to memorize which way it is, because if I try to memorize it, I've got a 50-50 chance of getting it right. If I think it through, I'm going to get it right every time. All right, so the way distillation works then is, let's say I'm starting, now this is a mixture of methanol and water, so in some chemical reaction, I've somehow created a solution that's 10% methanol. So I boil, so this is the liquid side, so I've got to boil it to make it into a vapor. And when I do that, the vapor is higher in concentration because the methanol is more volatile. We know that from Raoult's law. The vapor pressure of the methanol is higher than the vapor pressure of the water. So the vapor side, this is now the new vapor composition. And if we totally condense all of that vapor, then the composition won't change. And we come down to this liquid composition after it's totally condensed, and we boil that again. And then we condense it all again, then we boil and condense and boil and condense. And then we can see how we can get to a very high concentration of methanol. Now, if we wanted to do this in a more, slightly convenient way, we can just look at the vapor fraction, or vapor mole fraction versus the liquid mole fraction. And we get a plot like this. In many cases, this plot is quite common. And what you can see is a dotted line here where I've made a rough estimate of how this shape of curve looks based on the assumption of a constant relative volatility. So the relative volatility is this K value, which is the mole fraction in the vapor phase divided by the mole fraction in the liquid phase. And according to Raoult's law, this K value is P sat over P for that component. Well, if we take P sat over P divided by P sat over P, the P's in the denominator cancel, and this relative volatility, according to Raoult's law, is just P sat over P sat. But that P sat can change because you see here at the top of the distillation column, where the most volatile component is most concentrated, then the temperature is 65 degrees Celsius. And at the bottom of the distillation column, and that's kind of confusing, right? Because the bottom is up. All right, so this phase diagram, you have to think it through why it's this way. It's because the least volatile component has the highest boiling temperature. So at the bottom of the distillation column, which is the top of the phase diagram, the temperature is 100 degrees C. At the bottom is 65 degrees C, and P sat varies with temperature. So in order to get some sense of how the relative volatility is over the average of the distillation column, we've developed a rule. Chemical engineers have developed rules over the years, and they say, well, let's just take an average. But for some reason, I don't really even know the reason myself, they settled on a geometric mean instead of an arithmetic. So they just calculate the relative volatility at the top, relative volatility at the bottom, multiply and take the square root. That number I've done for this particular phase diagram with methanol, and the number is 4.1. Now we can use this Finsky-Underwood result, Finsky equation is really what it's called, to make an estimate of how tall the distillation column is. And so we simply plug in, what are our splits? The split is the fraction of the component that you want to go out of the distillation column as distillate. So the split for the methanol, we would like all of the methanol to go up, but you see what happens if all of the light component goes to the top of the distillation column, then that becomes 1 minus 1. 1 minus 1 is in the denominator is a very bad thing. So we can never really get to 100% split on the methanol. So we've got to pick something, 0.99. We'll pick that for this one. We don't want any water going out with our lovely product. Well, we don't want any, but we'll just set a tighter specification on the water split so that we get less water going out with our product methanol. And so we can put those numbers into that equation, and we get that 7 is the minimum number of stages. These are the stages if we count them off. 7 is the minimum number of stages that we require to do a distillation like this. So if we know that it's about 0.6 meters between trays to give enough space for the boiling liquid to disengage from the vapor so that the vapor then goes to the next tray, then we can multiply that together and we can get an estimate of 4.2 meters for the minimum height of the distillation column. But there's a problem because that's the lowest it could be, and essentially the result would be you wouldn't get any product. You would get a drop of vapor. It would be exactly the purity that you want, but you wouldn't have any significant process flow. So we need to convert from the minimum number of stages to some reasonable number of ideal stages. So we multiply by 2. You can see here I'm multiplying by 4. That's because ideal stages are an idealization. We don't really have perfect separation between the stages every single tray. And so we need another rule of thumb, and another rule of thumb is, hey, multiply by 2 again. So we multiply by 4, and we get the height of this distillation column. And then you can use some other guidelines that are still pretty simple, basically ideal gas law, to figure out what's the diameter of the column. Now we have the height, we have the diameter, that's the complete volume of the column. We have correlations for multiplying the volume of the column by the cost to determine the cost. And now we can compute the cost of this distillation column, add that up for 3 distillation columns in a reactor, and we have the complete cost for this chemical process. That's your basic chemical engineering in a nutshell. So what does that look like? This is what it looks like. This is clearly a distillation column. That's a distillation column. Oh, maybe I should have gone back. 16 meters, how tall is that? Well, about 3 meters is about one story tall, 1 floor of an apartment building, right? And so 3 goes into 16 something like 5 times. Throw in a couple of extra meters. So this is like a 6-story building tall. And so that's why we're seeing these big towers sticking up in our distillation column that are about 6 stories tall. I think these may be flare towers where you just burn waste products that you just want to get rid of. So that's your basic distillation column, and now we're ready to do some ABCD type questions to see if you have what you remember or what you've learned even just now, in case you didn't remember anything. Those long-term brain cells, how they've been working. And so let's talk a little bit about this phase diagram. It's a little bit strange phase diagram. You can see that it's got this minimum in it. How does that happen? Well, we're mixing this refrigerant. Refrigerants are made out of chlorines and fluorines, and they're polar. And things that have a dipole moment, that's a positive charge and a negative charge. They want to align their positive charges and negative charges and sort of stick together. Not like hydrogen bonding, but sort of weak hydrogen bonding. You could think of it that way. Whereas pentane is completely inert, it's in no polarity. And so the pentane and this refrigerant, they don't like to be together all that much. They will. They're not going to form a liquid-liquid split, at least not at this temperature. But they're not going to form an ideal solution. So we can understand this phase diagram even before we understand modified Raoult's law. The way we do that is we recognize that components that don't like to be together will want to get away from each other. So we don't, and when we add kinetic energy in the form of temperature, so the way I think of temperature is it's basically a square root of the sum of the mean squared velocities of the molecules. So when we add heat, we're raising the temperature, and what we're doing by doing that is we're causing the molecules to move faster. And the faster they move, the easier it is for them to break away from the liquid and fly off into the vapor. So that's the picture I've got in my mind when I am talking about this. So we're asking the question here, if these molecules don't like each other very much, do we have to add more energy or less energy in order to permit them to fly away? And the answer is less energy, because they're already anxious to get away anyway. And so that's what's causing the boiling temperature here to go down as we mix these molecules together. Raoult's law would say it should be more or less a kind of a straight line. So this minimum occurs at the point where it's a balance between their vapor pressure, which is trying to break them out of the liquid phase. The more the pressure is, the more they're trying to break away from the liquid phase. And then we're putting them together, and that's making them want to break away even more. And at some point, the molecules reach their minimum temperature, and this particular point is called the azeotropic point. And what you can see here, if this is the liquid and this is the vapor, and we keep going further and further here, as we boil this liquid and go to this vapor, boil this liquid, go to this vapor, we get to this point, we boil the liquid, and it's the same exact composition as the vapor. That means our distillation column is going to break. it's just not going to give us any higher purification. And now we've got a very complicated, much more complicated process to purify our components. And guess what? It's going to involve more distillation columns, and so maybe we're going to bump that up to 80% of the cost of the plant if we've got any azeotropic systems in our process. So that's why this phase diagram looks like it does. We'll do some more exploration of numerical evaluation of that kind of concept in a minute or two. But right now, I just want to see if you can interpret what this phase diagram means. So let's start with this point E and recognize that there are two separate pressures here. And we're going to answer, the question is always going to be about the nature and composition of the phases that are present on the phase diagram. So let me see if I can get a pencil here. And so A is going to be vapor, B is going to be liquid, C is going to be vapor plus liquid, and D is going to be liquid plus liquid. All right, are we ready for the Google thing you talked about?
Yes, we are.
Okay. So let's talk about point E at 1 bar. Is point E vapor, liquid, vapor plus liquid, or liquid plus liquid? Vote now. Any questions about the question?
So,
No, the question is clear, but where people is going to write down?
so what are the options again, please?
Okay, so A means that you think point E, so
Option A, it's a vapor. Option B
is at 1 bar. And what we're
Sorry?
going to do,
okay, liquid.
so what we're going to do is we go around this phase diagram. We're going to hit these points, A, B, C, D, E. And I'm starting from point E because I really think that's the simplest point. So let's do the easy one first. And so for point E at 1 bar, does it represent a vapor, a liquid, a mixture of vapor and liquid, or a mixture of liquid and liquid?
Okay, we are ready.
Are we ready?
Yes, the link is on the chat. People can answer there.
So let's give them, this is a pretty easy one. Let's just give them 20 seconds for this. I think it's easy. We'll see. If a lot of people get it wrong, we're going to have to talk about it.
Can I share my screen?
Sure.
We can see the results.
Oh, that'd be great. Oh, do I have to unshare?
Yes, please.
Okay, how do I do that? I think I'm in. Oh, there we go.
Okay, thank you.
I can do it. I can unshare your screen and allow.
So,
well,
those are the answers.
Okay, now I'm going to have to put my glasses on. Oh, wow. So it's about 50-50 between B and A. So
Maybe they are not clear. One pressure, it's very small. One pressure and 0.1 pressure. You know,
right.
which one they are talking about?
Right on the question that it was at 1 bar. I'm talking about at 1 bar.
Hey, 1 bar, one bar, 1 atmosphere.
Yeah,
it's not clear. It's not clear in the graph which diagram maybe we are talking about. Maybe
Yeah,
it's this,
I tried to write it, but my handwriting is horrible. So I'm writing sort of sideways. Let me see if I can clean that up.
be clear that you are talking about the highest.
Okay, so this is supposed to say 1 bar.
Should I give the screen to Elliott again?
Yes, please.
Oh, okay. So right now, this question is about 1 bar. So in other words, this diagram here is for 1 bar. This diagram down here is for 0.1 bars.
Sorry, Elliott.
You can see your screen. Share.
Thiago released the screen,
I
but you have
forgot to. Okay, so let me share it again. I always have trouble finding that button. Share it is there. Gosh. Okay, how'd I miss it? All right. So look here. You see, this is at 1 bar. The question right now is for E at 1 bar, and this is the diagram for 1 bar. This is the diagram for 0.1 bar. Is that more clear?
Yes. Now it's clear.
Okay.
Yes.
I'll unshare then, and we can go back and look how the results are changing.
Who wants to change the option? Please do.
I can reset.
Yeah,
I can
for some
erase
reason,
all the answers.
it's not letting me unshare. Oh, there it is.
No,
Look at it.
Judy, help him, please.
It's done.
So where's the graph, the chart? Oh, there it is. Okay, well, we're still, in that 40-40 range.
I think we should reset the
Okay.
graph.
I will clean every answers and we answer again. Okay?
Yeah.
So let's answer again, please.
Okay, everybody vote again.
Where's the
Same link?
Yes, the same link, please.
Nice touch with the picture, Thiago.
Thank you. We are professionals here. Very different results.
I think in the future, we probably shouldn't share the answers until maybe about 20 or 30 seconds after we've sort of let people have a chance to think. You know what I mean? Because I think people might see, oh, most people are saying, B, and then they go with the flow.
You are right. You are right.
Look at the speed here. But the good news is that with the clarification of the question, the answer is a lot more right. Yes, B is the correct answer. Okay, so now I'll try and share again.
Okay.
And just clarify. Am I sharing yet? So if this is vapor for this curve, then below that curve, what you can do is just try to imagine, ignoring everything below this line.
Not yet.
All the stuff down here doesn't exist. And
You're not sharing yet.
This is, I'm not sharing yet? Darn. That's what I did. Okay. So if it helps you, just imagine ignoring everything below this line when I'm talking about the phase diagram for 1 bar. And when we're talking about at 0.1 bar, ignore everything above this line. And this is the way these kinds of more complicated phase diagrams work. And what's happening here, as we go to colder and colder temperatures, the molecules don't like each other. They begin to hate each other so much that they don't want to be together. Even if they can't escape to the vapor, they're going to just go into their separate rooms, slam the doors, and not talk to each other. So you may know some family members who've gotten like that in the pandemic crisis, right? So, so there's a lot of ways that molecules behave that we can understand from a really humanistic perspective. We could ask the question again for point E at 0.1 bars, but I think people probably would get that when you change the pressure, you make the pressure lower, then something at this temperature then is going to be vapor, because relative to this lower pressure, I don't need as much energy to push the molecules into the vapor if the vapor is at such a low pressure that it's pulling the molecules towards the vapor. So that's why the temperature here is going to be all vapor. So let's change the question a little bit. Whoops, what happened? So let's talk about no. So let's talk about
Point D is a good question.
point D. Point D, that's a hard one. We'll get to that one later. Yeah, I was going to try to use the typewriter because my handwriting's so bad, but it was too small. So let's go to a slightly more complicated one. Let's do point A now. And let's do it at 0.1 bars. Are we ready to vote? Should I stop my share? Oh, wait.
Same options?
Start voting. Start voting. I'll stop my share in 20 seconds or so.
Okay, the same options?
Same, A, B, C, D. Is it vapor? Is it liquid? Is it vapor plus liquid? Or is it liquid plus liquid? Any
Okay,
questions
just a
about the
minute.
question? Is the question clear?
Yes, just a minute.
I'll go ahead and stop my share. You just don't start your share yet for another 10 seconds or so.
People, same link, okay?
Yeah, wait until you get to about, let's say there's 30 students, 37 students. When you get to 30 responses, then you can flash it up, I guess.
Okay.
Oh, it looks like we've got 51 participants now.
And Dr. Elliott,
Yes?
Professor, if you need more white space to draw, I sent you a link in the chat of the Zoom app that goes to the Google Jamboard.
Oh,
So if you need more white space to draw, not together with the diagram, but other things, you can try that. You can click the link and you will draw on your browser and you share your screen and we can see it.
well, there's this thing called whiteboard. I could try that.
Oh yeah, the Zoom also has the whiteboard. That's true.
Oh, I didn't know Zoom had a whiteboard.
Yes,
I'm
yes.
looking at my Windows whiteboard.
Go to your share screen button and then choose whiteboard.
Oh, okay. Okay, share screen. Oh, I see, whiteboard, yeah. Okay.
Yes.
All right. Well,
Can
I
I
guess
share?
we should just check the voting for now, though, right?
Let's check. So just a moment. So this is the question. How about point A at 0.1 bar? And well, those are the answers.
So most people thought vapor plus liquid.
Yes. options.
Democracy is a great thing. Democracy got it right this time. Most of the time, democracy works. Okay, so this is true. This is the correct answer. Great job, guys. All right, so we're understanding each other, but we can still get to 100%. We can do better. Let's see if I can share again. and we'll go ask the next question. Oh, I can't share yet.
Can you share your screen?
I
already shared mine.
Oh, okay, okay. I thought when I
Yeah,
clicked it, I couldn't do it anymore. Then I was okay. Well, this is going. I think people are getting the idea now, and we don't want to spend the whole day on this. So let's see if we can sort of wrap up. And Professor Tavares was interested in this point D. Honestly, well, let's see what people say here.
Well, we have no options for that.
Actually, that's true. I was just getting ready to. It would be kind of pointless because I would have to add E.
Oh, sorry. Sorry, I ruined this. Sorry.
So yeah, E. So it's actually a case where it's a vapor liquid equilibrium point, and it has to do with the Gibbs phase rule and a lot of different things going on. That it's actually just a single point here where the vapor, liquid, and liquid are all in equilibrium at the same point.
My bad, sorry.
I should have thought about it at the beginning. If I put the E on here, then maybe we could have gotten that one in. I just didn't think about it. All right, so now we've had some fun with phase diagrams. I think we're understanding each other better. That's great. I'm happy with that ABCD capability. So now the question is, where do these phase diagrams come from? We're engineers. We walk up to a chemical plant and we say, I've got to design that distillation column. I'm going to need a phase diagram. And the technician looks at you and he goes, what's that? So as the engineer, you're on your own. You've got to build your own phase diagram. So how are you going to do that? And it turns out there are some magic words that we can say. Like, you know how magicians say abracadabra? So I'm trying to think of, I don't know, in Brazil, do you have magicians or whatever, and in the United States, for some reason, they say abracadabra, that's the magic word. And then they open the box and there's the pigeon, okay, or the dove, and it flies away. And so that's what magicians do, right? And so this is kind of a similar situation. We need some magic words that we can say and then magically solve for this phase diagram. And I'm wondering if you remember what those words are. How do we solve for a phase diagram? And before I show you the big reveal here, I want you to think of your favorite magician. And I'm thinking of mine. And it's a kid with a bad haircut, and he's got glasses kind of like these. Do you know who I'm thinking about? Before I show you, you got to remember what I said early in the slide about Bloom's taxonomy. There are certain things that promote long-term memory, and they may not be the things you think. Sometimes somebody tells you a stupid joke, and it's such a stupid joke, you could never repeat the joke, but you can never forget the joke either. It just sticks in your mind because it's stupid. Okay, so stupid things can help your memory. And so that's why I thought you might enjoy a slide like this. Okay, so if Harry Potter was a thermodynamicist, then the way he would solve for a phase diagram is he would say fugacitate, and then the phase diagram would appear. And what that meaning of fugacitate would mean is equate the fugacities. That's how we solve for phase diagrams. And a simple example of that is Raoult's law. We'll show how Raoult's law leads to the equating fugacities. And then here's a diagram that comes out of applying Raoult's law for pressure versus composition of methanol and water. What pressure? I mean, yeah, okay. So we know the temperature here is 65 degrees Celsius, how do we know the boiling temperature, that this is the boiling temperature of methanol? And the way we know that is that this number here is about 760 millimeters of mercury, and we know that 760 millimeters is 1 atmosphere. All right, so all of these things go together, but this gives us a chance to talk about a slightly different phase diagram where we're plotting pressure on the y-axis instead of temperature. And so now somebody forgot to label this phase diagram. So is this point right here? Well, I guess I already told you. That's the boiling temperature of methanol. So to properly label that, I should write nope, that's wrong. This has to be a P. There we go. So if I'd written T there, I would have gotten a wrong answer there. So these are phase diagrams, are things that the professor can throw on the test and say, hey, label this phase diagram. And if you do it wrong, you will lose points. It's a very simple question to ask, and it's a little surprising how many people will get it wrong. And so you need to be a little bit particular about labeling each point. And another thing here, is this vapor or is this liquid up here? Let's do a ABCD question. I'm going to give you a hint. It's not C or D, okay? And it's just, is this a vapor or is this a liquid? So what are we going to call this? We'll call this point A. So is point A, worst X ever. So is this, X marks the spot. Is that point vapor or liquid? Vote now. I'm going to give
Just
you
a moment, please. I'll update the link. Just
okay.
So option A, vapor. Option B, liquid, isn't it?
That's it.
So you gave us a very good hint. It's not option C or D.
Yeah. Making this question so easy for you.
I've never thought about fugacity as a spell before. So just a minute.
I'll stop my share now, and then you can control when you want to display it based on the number of responses.
Okay, so the link is the same and it's updated. You can vote now, please. Let me see. So here's the question. How about point A? Option A, vapor. Option B, liquid. Let me unshare just to check if people have
So I
already.
can't see your screen, Thiago.
Can you see it?
I can't. I don't know if the students can.
Okay, let me unshare it just to check the answers before I show it. Come on, people, answer it.
Flip a coin if you have to.
27. Come on, 28. Let's answer. Almost there. 32. Okay, I think we can show the results.
Okay.
So just a moment. So that's the question again. And these is the answers.
Wow. democracy has failed. Wait. Yeah. Wait. No, I got it backwards. I have failed.
What happened?
Okay. Yes. The democracy worked. I'm sorry. My bad. I got confused. Yeah. So let's see if I can go back to sharing then, and I'll talk about that. Oh, I can't do it quite yet.
You can now.
Now I can. I'll try again. I'll click here, and so yes, it is liquid, and so we should write a big L here and a V down here. And the reason that we know that is, again, following the process, not trying to memorize where the points are. But if we follow the process and we take to extreme pressure, if I put, 1 million bars of pressure on something, it can't be a vapor anymore. All right. And so it has to be a liquid if I'm starting from way up here. So this must be the liquid side and this must be the vapor side. Whew. All right. So good. Most people got it. And so we're moving on. But now we have to learn to create our own phase diagrams. And so let's then sort of get a running start then and go back to talking about modified Raoult's law. And the way I want to do that, and I've already talked for a very long time, so I don't know how much longer I've got. Fred, could you pipe in there or let me know?
What you mean for long? The time?
Yeah,
you
how
can
much
go.
time do I have?
You can go. We use maybe you leave like 10 minutes before noon. We can ask something, or 15 minutes before noon.
Oh, okay. So another hour or another 40 minutes from now?
Yeah.
Oh, okay. That's
If you
great.
want.
I think I was afraid maybe I only had 5 more minutes or something.
No, you can.
Okay. All right, great. I'll take some time then. So if you've ever seen the front cover of
Elliott.
the book,
Elliott.
students in this class, are they using this our book, the yellow book? Fred?
Elliott, if you want to stop earlier, we can use for questions.
Oh, okay. Well, I will. I'll try and wrap it up in 20 minutes. That's my goal.
Okay, good.
But I had a question for you. What are the students familiar with our book, the yellow book? What are they using in their class?
Well, in the undergrad, they use a Smith Van Ness book. Is it what you are asking?
Okay. So they would know everything about Smith and Van Ness.
Yeah.
At the graduate level, what book are they using?
Undergrad, they had the undergrad using Smith Van Ness book. Is it?
I'm talking about the graduate course. They're in a new graduate course.
No, they're starting. They're not used yet.
Oh, they're not in any course.
No.
Oh, okay, I'm with you. All right, so then you might not. The students probably haven't seen this picture before, so I think I should go into some detail. This picture is on the front cover of the textbook that Carl Lira and I wrote, and so what it shows is the results of quantum density functional theory calculations of the electron density on the surface of various molecules. And I think if you look at this one, you won't be surprised at least to see that we've got 2 blue things. The blue things correspond to positive charges. So these are 2 protons, and a big red spot over here is a zone of high electron density, so negative charges. So you would expect oxygens to do that. And so this is H2O. This is water. And you can see we've got a lot of waters in this picture because water is a pretty interesting molecule. And in general, the red is lining up with the blue because the negative charge wants to be associated with the positive charge. That's the way we'd expect things to line up. And so here what we have, this smaller molecule with one red and one blue, that is a methanol molecule. This molecule here is slightly bigger than the methanol molecule, but it's got the same red and blue. That would be ethanol. This molecule here, you might not be able to see it from both sides, but this is essentially octane. Okay, so there's 1, 2, 3, 4 big bumps here and 4 big bumps along this edge. So that 4 and 4 is 8. This is octane. These two molecules here, what you can see is the one on the left has a positive charge, but not a negative charge. The one on the right has a negative charge. You know, it's got to average out, but the positive part of it is so smeared out, it doesn't really make a dark blue area. Similarly, there must be a red or pinkish part over here on this molecule, but it's very spread out. Can you think for a minute what molecules these might be? So what has a lot of carbon content? That's the green. These are CHX types of things. And then it's got a big oxygen on it. I'll just tell you, these are 3 carbons here. And then this oxygen is sticking off to the left. That would be acetone. If you think about the molecular structure of acetone. This molecule here, I'll just let you know, these greens in this case are chlorines. Chlorines are similarly inert. They just don't have positive or negative charges on them innately. They are electronegative, so they can draw electron density away, but they can't really hydrogen bond on their own. So these are 3 chlorines, a carbon in the middle. Carbon can form 4 bonds. If 3 of them are taken by chlorines, then we've got an H left over. So this is CHCl3, also known as chloroform. And so chloroform has this 1 proton left over with these strongly electronegative chlorines on it, pulling the electron density away from that proton and making it a really stripped naked positive proton. Normally, if you've got hydrogens all along your octane, there's no electronegativity in the alkane chain, so there's no drawing the electrons away. So you would not expect a hydrogen bound to a carbon to have any hydrogen bonding capability. But chloroform, because of those chlorines and being so electronegative, is a special molecule that leads to this kind of blue-red energy of interaction. So that's some of the basics of hydrogen bonding that we can understand just by looking at these electron density plots. These electron density plots are made by just doing calculations of individual molecules by themselves. So we're not looking at combinations of molecules 2 together. It's individual molecules by themselves, but we can look at the picture and we can easily understand how those molecules are going to interact. And that's the kind of perspective that I'd just like to get across today. I'd like to combine that perspective with the Lennard-Jones potential. Maybe you've heard of that before, but essentially, if you haven't, all it does is it recognizes that you can't put 2 things in the same place at the same time. So the energy, so this is a work function, essentially. Work has units of energy, and it's the work of putting 2 molecules at this distance r. And this distance here is 1.0 on this scale. And so that means that r is equal to sigma. Sigma is, you can think of that as the diameter of the molecule. So when you try to put 2 things in the same place at the same time, what you see is that the work you have to do to achieve that is becoming infinite. And a simpler way of saying that is you can't put 2 things in the same place at the same time. And that's reflected mathematically by this work function going to infinity. On the other hand, if you want them to be somewhat close together, they do stick together. So once they're stuck together, you've got to actually put in positive work to rip them apart. So this is your basic way that molecules interact. the Lennard-Jones potential is only a function of distance. So it represents an averaged interaction if you took these molecules and you spun them around in spherical coordinates so that there was no orientational preference for these molecules to interact. So the Lennard-Jones potential is a kind of a simplified representation of how they interact when you average them out. We can make a simplification of the Lennard-Jones potential to help us understand the interactions a little easier. One version of that is the square well potential. So it's pretty simple. It just says the work of putting two things at the same place at the same time is infinite. It means mathematically, we don't allow that. If they stick together, then there's this energy of having to pull them apart, and that's reflected by the depth of this square well. But if they're far enough away, they don't have much of an interaction. These interactions die pretty quickly. And with a slight extension, you can understand how two different molecules would interact on the same graph. So this is the potential function square well for, let's say, molecule 1. And you can see it's just a square well, just like this one. And what I've done then is make another square well for molecule 2. You can see that molecule 2 is bigger than molecule 1. Its repulsive diameter is bigger. It's also stickier. It's got a deeper well. So I'm going to have to do more work to pull these molecules apart. Now, if I don't have any kind of molecular tweezers, how do I inject energy? Remember, work is energy. How do I inject energy to rip these molecules apart? The answer is temperature. Temperature is energy. So if I add energy, I'll be able to send these molecules from this distance, in other words, very stuck together, close together, to distances out here far apart. If you think about that for a second, you'll understand that these, when they're stuck together like this, that's a liquid. That's where they're all very close together. And when I pull them apart, that's a vapor. So it's the same concept that we were just talking about with the phase diagrams, just translated into a molecular level. Now, there are some molecules that are going to like each other and some molecules that are not going to like each other. Let's just talk about the ones that like each other. What you can see here is that the chloroform, if I was to mix chloroform with chloroform, in other words, it's just a pure chloroform fluid, then these blue places would not really have a place to go. They would just bump into other blues, or maybe the backside of the chloroform. And whatever they do, it's a pure fluid, so it's an ideal solution in some sense. And so it just is a mixture of chloroform with whatever interaction chloroform has. And similar for acetone as a pure fluid. But a very interesting thing happens if I put the acetone with the chloroform. They're going to like each other. And that means their energy of attraction is going to be greater. They're going to want to stick together. In other words, I'm going to have to put more energy to pull them apart than I would if they were just by themselves. Or maybe a better way to say that is if I was to mix two molecules that didn't like each other, then I wouldn't have to put as much energy to pull them apart because they already hate each other trying to get in anyway. So that would be the scenario like the refrigerant with the pentane that we talked about earlier. This is the opposite situation where they like each other too much. So now let's go over here and let's talk about what we would expect the interaction potential to look like for two molecules that like each other. What we can see is the distance between them is going to go to infinity halfway between. Why is that? Well, if you've got a small molecule and you've got a big molecule, the radius is half the diameter, so it's half of sigma, right? And so this is sigma big over 2. This is sigma 2 divided by 2. This length here is sigma 1 divided by 2. If you add sigma 1 plus sigma 2 divided by 2, you get halfway in between. So this graph is pretty easy to understand, this part of the graph. The only part that's left is how deep is this well? Because to get where it goes up again, we just multiply the repulsive diameter times 1.5. So that's how the square well fluid works. So we know this part, we know this part. The only thing left is to figure out what's this part. How deep is it? So we've got a way of describing that. This is the way chemical engineers do this. They take this representation of the depth of the well, that's epsilon, for a 1-2 combination. They say, let's use a geometric mean on that. Okay, fine. So we multiply and then take the square root for the 2 individual pure components. Then we multiply that times the correction factor to say, well, some molecules like each other, some molecules don't like each other. Let's figure that out. But it's confusing because it's 1 minus Kij. So we got to think it through. Is making Kij positive, is that going to make they like each other? Or is it going to mean they don't like each other? We have a choice here. We have A, B, and C. Let's call this one A. Let's call this one B. And let's call this one C. So for acetone and chloroform, which one of these K12 values describes the interaction best? Any questions about the question?
Will we do a Google form?
Yes, please.
So just a minute. So option A, it's actually minus 0.2.
No, actually that's a positive sign. Option A is K12 equals positive 0.2.
Okay, option B
is K12 equals 0. Option C is K12 equals negative 0.2.
Okay, just a minute.
And the mixture is acetone plus chloroform.
Just a minute. Okay, people, the same link. We are ready.
All right, I'll stop my share, but you don't share yours until you, oh, you know that part, right?
Okay, okay. Let's go. Let's see. Let me share my screen.
Are the answers a little slow?
Yes, a bit. So this is the question, mixture of chloroform plus acetone. Come on, people, let's answer it. Let me unshare just to check the number of answers. 29.
Oh,
You can do better. Come on. 30. 31. Almost there. 34. 35. 35. I think we reached the maximum of answers.
Okay, yeah, I noticed we went from 51 to 49 participants. Probably a couple of students dropped out.
Yeah, not everybody in this room is a student. There are a few people from our lab.
Yeah, so we just don't know.
So let me share the screen again. Let's see the results. So those are the results.
Okay, so most people went for option C, and democracy has succeeded. All right, so that's great. Let me go back and share my screen again. I'll just kind of reinforce why that's the answer. And it's easy to get this confused the first time. And so what you got to realize is that we want this depth of the well. We want that to be larger in magnitude to reflect that they're stuck more together. All right. That part can be confusing by itself because the depth of the well is a negative number to begin with, but we're representing this depth as a positive number, okay, that just represents the magnitude of the depth of the well, not the direction of the depth of the well. So that's one of the things that people can get confused about. All right, so this epsilon just represents the distance from the 0 axis here to how far down did we go? What's the depth of this hole? If they stick together more, then that hole is deeper. So we have to pull harder to get the molecules out of that hole and pull them apart. To reflect a bigger magnitude here, you need a negative sign so that minus of a minus becomes a positive, and then this becomes a bigger number, and which represents a deeper well. So there's a lot of ways to get confused here, and I'm not surprised that you would do that. But again, you got to remember the process. The process is the epsilon here is the magnitude of the depth of the well, and a negative of a negative makes that magnitude bigger. But let me say this about that. Acetone and chloroform are the exception. In most cases, this K12 value will be positive. And so don't try to memorize, oh, it's negative all the time. No, that will do you wrong. You need to think it through. Think about, if I want to represent weaker interactions, and here's a good way to do that, to take the extreme. Imagine if K12 was equal to +1, then the depth of that well would be 0. And it would just be a hard sphere, right? It would be 0, 0, 0, 0, then boom, infinity. You can't put those two things together, but they have no attractive energy for each other. That actually never happens. But the depth of the well could be quite small. So K12 could be, 0.9. That would be pretty extreme, but it's possible. So let's see now. For some reason, it's not scrolling. Let's see. Here we go. So now we're ready to do the real engineering part and get into the mathematics of things. So if we look at our entropy of the mixture, then even for an ideal mixture, then we still have this result for the entropy of mixing. In other words, the disorder increases just by virtue of the molecules being all mixed together, and the idea that we have to separate them apart. And this result we can actually solve from looking at the ideal gases. But if you used Smith and Van Ness, then you probably haven't seen how to derive that function, but at least you've seen it before. But really what's happening here is the molecules are intermingling, and so there's more disorder, and so we would expect the entropy to change. Why is this a negative sign? Well, it's because the log, the mole fraction is always between 0 and 1. And the log of something less than 1 is less than 0, right? And so this log is going to be a negative number multiplied by a negative number. Got to keep track of all these minuses and minuses, okay? And so that becomes a positive number. So we see that the entropy increases relative to a simple molar average. So when you're thinking about some kind of diagram of entropy versus composition, then this part is just going to be a straight line, and this part is going to be a positive hump. All right, and so there's that part for the deviation from the straight line. So the entropy is not a straight line, even for an ideal solution. For the energetic part, we could make this an ideal solution by setting this parameter Aij equal to 0. If it's 0, then the heat of mixing is just the simple molar average, and that's called an ideal solution. That mark we always know. And so the deviation then from the ideal solution and the actual solution is just this yellow part, and that's what we call the excess enthalpy, or the heat of mixing. And since the excess, so the excess is always relative to the ideal solution, since we're using an ideal solution model for the entropy part, the excess entropy here is 0, and the excess enthalpy is significant, but G is H minus TS. So if S is 0, then G is equal to HG. And so our model then for this heat of mixing is just this quadratic formula, and that is the Margulies model. When we take the derivative with respect to composition to get the fugacity of the component in the solution, and for some reason the font mixed up when I went to print this. So those should be hats, right? So the hat means this is the fugacity of the component in the mixture. And we see that for an ideal solution, that's just YIP or XIP. But for a non-ideal solution, we have to throw in this fudge factor, the activity coefficient. So if the activity coefficient is just 1, we recover Raoult's law. And we can compute the bubble pressure then by just taking the sum of the xi, gamma I, pi sats. Then we go to distillation. Our alphas are going to be different now because the K includes gamma there's something missing here. So
Pressure
yeah,
is
the vapor pressure should be here. Pi
yeah, and the
of
pressure.
light D, right? Because it still should be Raoult's law when the activity coefficients are 1. So there's a typo here. So you got to multiply that. That's supposed to look like a star or a multiplication sign. Okay, so this is P1 sat. Oh, okay, so this should be PL sat. And this should be sat. And this should be H. There we go. Horrible handwriting. I'm actually writing with the mouse right now. All right, so this is fixed now. And so that's Raoult's law. And if we had a different model for how these how this excess energy changed, then we would have a different derivation to get to the activity coefficient, and that would give us different results. So for instance, this is called the Flory-Huggins equation, where instead of using mole fractions, which would be the Margulies equation, we use volume fractions. So that's what these capital phi's correspond to. So regular solutions keep the excess entropy equal to 0. Flory-Huggins solutions make an estimate for what the excess entropy is, as well as what the excess energy is. So you can see how we can develop many different models very quickly based on how we think the solutions behave. The Flory-Huggins part is important for polymers because the volume of a polymer relative, the molar volume of a polymer relative to the molar volume of a single molecule, the polymers are much, much larger, right? And so we can understand quickly why the entropy, which depends on these volume fractions, is going to be very different when ratio of volumes of the molecules is really, really different. And the process of solving for LLE or SLE or VLE is very similar. Once we've got our K values, we solve our flash equations, and we get the amount that's vapor, the amount that's liquid, and we can do all the phase diagrams and the phase amounts and the phase compositions using those kinds of flash calculations. With when you're talking about liquid-liquid equilibria, the PSATs drop out because these are liquid compositions, and the liquids are not sensitive to the pressure. And we can see that better if we understand what's the derivation that goes into Raoult's law. So let's take a look at that. We have the Gibbs energy for the mixture, and so then the Gibbs excess is here. If we expand out the definitions, the first thing we have to do is recognize that there's an N in the denominator of our total Gibbs energy. So when I put an underbar under the G here, that means that's the extensive total Gibbs energy, and I'm going to explicitly represent the number of moles here like this, okay? This is a G without an underbar, so this is a molar Gibbs free energy, and it's for the pure component I. And what we recognize is that the chemical potential is essentially the Gibbs energy for the component in the mixture. And so this total Gibbs energy is equal to the sum of the chemical potentials. So I can move that inside the sum, and it gives me this relationship then between the mu I and the GI, which I can write as that through the definition of the fugacity in terms of the chemical potential. I can write that as the log of the fugacities over the log of the pure component fugacity. This is the pure component Gibbs energy. And we recognize that as the definition then of the mole fraction times the activity coefficient. So through that kind of analysis, we recognize that the Gibbs excess energy is the sum of the mole fractions times the logs of the activity coefficients. And if those activity coefficients are all equal to 1, then the Gibbs excess energy will be equal to 0. And that makes perfect sense because 1 is the activity coefficient for an ideal solution, and 0 is the excess energy for an ideal solution. Now we can turn that around, and this is where we get to have a lot of fun with seeing if the students have actually understood all of these things that we derived. Because if we just ask them to perform a calculation with a given activity model, that shows that they've learned the procedure, but they haven't learned where the procedure comes from so that they could develop their own procedure, their own activity model. And so to assess whether the students have achieved that next level of Bloom's taxonomy, what we have to do is give you an activity model that you've never seen before, and then ask you to apply this approach where you take the model of the Gibbs excess energy, take the derivatives, and develop an expression for the activity coefficient that you can then plug in and create your own phase diagrams from a brand new activity model. And so the key then is to take the derivative of this Gibbs excess energy, but the mistake the students always make is they forget, and I make it too sometimes, don't forget, I'm a human being. And so it's not uncommon to forget to multiply the Gibbs energy, the molar Gibbs energy, by n before you take the derivative, because these derivatives have to be with respect to n, not with respect to x. All right, and so you have to go through these derivations. And just to show you how it works out for this relatively simple Margulies one parameter model, when you write it down for just a binary mixture, this is all it is. It's the simplest model you could imagine. We know that the excess energy has to be 0 when the mole fraction is equal to 0. In other words, it's pure component 2 when x1 is 0 and component 2 is 1.0. So there can't be any excess when it's a pure component, right? So we know it has to be 0 when it's pure component 2. By the same argument, it has to be 0 when it's component 1. So when x1 goes to 0, x2 is 1. When x2 goes to 0, x1 is 0. So this very simple rule is the most trivial model that you could put together that would just match those boundary conditions. And it results in just one parameter, and that parameter decides how high the deviation from ideality is. All right, so let's think about this, this picture of the molecules, and let's think about whether they like each other or they don't like each other. So which one is going to correspond to they like each other or they don't like each other? So let's say that this is A and this is B. So B for blue, right? So the blue curve corresponds to choice B here. The red curve corresponds to choice A. And I want you to answer the question, which one corresponds to the molecules liking each other?
Just a minute.
I'll stop my share now.
Okay, we are ready. Same link.
Yeah, so we could write the question as, for the Margulies one parameter model, which one corresponds to the molecules liking each other? A12 equals +4 or would be A, and A12 equals -4 would be B. Got it.
Great.
The parameter with A equal 2 is the limit for liquid equilibrium.
Well, we'll just talk about liquid-liquid equilibria later, yeah. But yeah, we don't want to give any hints about the answer yet.
Come on, people. So 26. We can do better. Come on. $27, 28, 'almost there. 29. I think they are still thinking about it.
They were taking a
Yes.
nap, and then all of a sudden I zapped them with a question.
30, 31, almost there.
Oh, we're down to 45 participants, so we might have lost 4 more students.
32. 33. 33. I think 34.
Okay, let's give up.
Okay. So this is the question. And let's see the answers. So these, oh, I'm sorry. Oh, This is the answers.
So most people chose B.
Part B.
That is the correct answer. Hooray for democracy. Okay. So let's go back to the question then, and I'll clarify why, and I'll give you a really easy to remember, but it's easy because it's stupid way to remember when they like each other and when they don't like each other. So the answer is B, and it's negative pretty much for the same reason that the K12 was negative. All right, it means a deeper well of attraction. When when an energy is negative, that means we have to add energy to pull them apart. Okay, and so the negative A12 goes with the negative K12, and maybe that helps you to understand why they chose the sign conventions that they did. All right, but an easier way to remember this is to remember if they like each other. This is a smiley face, right? So if it's smiling, they like each other. All right, so it's stupid, but it's an easy way to remember that when the excess energy curve, the Gibbs excess energy curve is smiling, then the molecules like each other. So hopefully you'll never miss that one again. So let's take an example here then of here's a Gibbs excess energy model. Let's show how to derive the activity coefficient for that model. And notice that the first thing that I did was I recognized this quantity N and I separated from the extensive Gibbs free energy. So then I cross multiply by N, get everything in terms of values of N so that I can take the derivative with respect to N1. Well, N2 at constant N2 is not a function of N1, but N1 plus N2, maybe it helps to write this. N in total is equal to N1 plus N2. So yeah, that's a function of N1, but it's a pretty easy function. So I can take the derivative of that with respect to N1, it's just going to be 1. But because this is a product, we have to apply product rules. So let's hold this denominator constant, and we'll take the derivative of the numerator. Well, dn1 is just 1. And then we'll hold the numerator constant, take the derivative of the denominator, it's negative 1 over n squared, dn1. And or dn1 plus n2, where n2 is constant with respect to n1. Again, that's just 1. All right. And so now I can factor out, I've got a 1 over n here, I've got a 1 over n squared here. I can take 1 over n outside of the parentheses, distributive law, and I've got n2 over n times 1 minus n1 over n. Well, what is n2 over n? What is a simpler name for that? How did we get from here to here? Well, we plugged in the definition of the mole fraction. N2 over n is just mole fraction of component 2. And by the same reason, this is the mole fraction of component 1. But 1 minus the mole fraction of component 1 in a binary system is just mole fraction of component 2. So let's just write that down. That's our activity model for this Margulies model. So very, very simple. And the process that we go through for every other activity model is exactly this process. The derivatives get a little more complicated sometimes. Now we're ready to take that activity coefficient, which we know the definition of in terms of the fugacity, and equate the fugacities of the vapor and the liquid by representing this K ratio of yi over xi in terms of the ratios of the fugacities. And then when we solve the equations for the mole fractions in the flash form, then we will effectively be equating fugacities. And when we do that, well, this one's actually an easy way to see if YIP is the fugacity of each component in the vapor phase, and XI gamma IPI sat is the fugacity of each component in the liquid phase, then just sum the left and sum the right, set those equal to each other, and that must be equal to the total pressure P. So that's a very easy one to understand how we're equating the fugacities to arrive at the solution. And Harry Potter is happy, and we're able to generate phase diagrams now. So let's go take a look at how those phase diagrams might come about. And if you don't have a spreadsheet like this, it's very easy to build. I don't like to just give the spreadsheet out. You learn a little more about what's going on instead of a black box. If you build the spreadsheet for yourself, I think engineers should be able to build things, and spreadsheets is one of them. But if you want some help, there's this kind of YouTube approach where you can watch some tutorials on how to do that, and that's posted at this website, chethermo.net. So I've typed in here methanol and water, and one thing I did was, for now, because I was making those graphs that I showed you earlier, I set the A12 value equal to 0. But according to the MAB method, that interaction could be 273. Okay, and so in order to get the activity coefficient, I actually need to divide the A12 times RT, divide that by RT, so that I've got just A12. And there are different opinions on whether you should say that A12, how to define it. Should it already include the RT or should it not include the RT? We made a decision. I'm not sure it was the right decision, but we decided that A12 includes the temperature as part of it, but the energy of interaction between the molecules, that does not have temperature in it. That's a fundamental property of the molecules. And so when we want to estimate what's the energy of interaction of the molecules, we have to compute something that's not a function of temperature. So that's why we first compute this quantity without the temperature in it, then we have to divide it by the temperature to get the quantity A12 that we use to do the calculations. So this A12 over RT, or this A12 value is dimensionless, okay? And I can change the temperature here and get various different pressures. The method of estimating the vapor pressure here that I'm using is what I call the shortcut vapor pressure method. So it's just in terms of critical temperatures and critical pressures. It can be a little bit off. So this is an estimated value. If you want to put real, accurate Antoine coefficients, you can just paste those in here instead of just using the formulas in terms of these generalized Antoine coefficients in terms of the TCPC and omega. So this is an estimate. It's a prediction, not an actual value. When I was making the graph for class, I wanted to use what I knew was the true boiling temperature of methanol. But in general, I'm just going to set, this equal to its predicted value. I was already using the predicted value for water. But we could change the temperature, and you can see how your phase diagram is going to change that way. So as you lower the temperature, the pressures on this axis go down. As you raise the temperature, 348. Yeah, that's where we started. Okay. And so to see where I got that graph that I just showed you, set this equal to 0, you can see that 273 doesn't really make a huge amount of difference. So this methanol water solution, we're expecting that to be fairly ideal. But where's this MAB prediction coming from? This is the Margulies model. So when I go to calculate my activity coefficients, you can see all I've done. So we had that expression that the log of that quantity was equal to the x1 squared, or mole fraction, or activity coefficient of component 1 is x2 squared times the A12, this A12 times RT divided by RT. Okay, so I wanted to go direct to the the source here, and so I use that directly. And gamma 2 is the same thing backwards, except that we're using mole fraction of component 1 squared instead of mole fraction of component 2. When I go to compute pressure, it's just the sum of the xi gamma I well, x2 is 1 minus x1. These are the gammas, and these are the pi sats. So you can see that this formula that I'm using to create this phase diagram is exactly what you'd expect. The yi is just equal to the x1 gamma 1 p1 sat divided by the total pressure. And so there's no magic there. And you can see then how I've generated this phase diagram just by writing these equations in here. But what if it was ethanol and water? All we got to do is change one letter. All of a sudden, there's some more curvature to this result. What if it was octanol and water? Ooh, did that wrong. Octanol? Yeah, then we see all sorts of weird things are going to happen. What if it was propanol? Oh, it doesn't exist again. Just call it propanol. There we go. So when we've got propanol, we see we're starting to get an azeotrope, but it hasn't formed liquid-liquid equilibrium. Octanol and water, when you see the pressure diagram go nuts like that, that's an indication that you've got liquid-liquid equilibrium. And so that is something we need to talk about. And Fred gave you a hint about that when A12 goes to more than the value of 2, that's when you expect to see liquid-liquid equilibrium for the Margulies one parameter model. All right, so propanol, no liquid-liquid equilibria yet. So what about butanol? How did I spell that? Not that way. I must have started adding in there. Yes. So within butanol, A12 is still not quite beyond 2. I don't know if I have hexanol in here. Nope. Well, let's go back to octanol. And we can see that A12 is now 4, which is a lot more than 2. And we can see we've got this indication of liquid-liquid equilibria. And that corresponds to the hint that Professor Tavares gave you. If you want to know where are these numbers coming from, what I've done is I've made a table of all the different properties. And this is listed at that chethermo.net. If you want to just download the properties, they're all here. And then what I've done to look up those properties is use the VLOOKUP over to that props spreadsheet. And so that's how I'm able to change the compounds quickly and easily. And let's go back to methanol. And everything's good again, okay? We can also do the same thing for the TXY plot. And you can see that I've done that here. Really what I have to do is I have to set the pressure, and then I can call the solver to determine whether the mole fractions of the components sum to 1 with this particular set of estimates for the temperature. And so solve for the set of temperatures that satisfies all of that. What I can do is set an objective function, which is the deviations from unity as the mole fractions, and sum that for all the different temperatures, and then minimize the deviations all at once. And again, there's a video how to do this if you want to learn how to do it. Sometimes this latest version of Excel, it just wanders off. It helps if I just switch. I don't know. The solver seems to be lost. Oh my goodness, the whole thing is lost now. I think my Excel has crashed. Well, that's going to bring this lecture to a little bit of a quicker end. But I think you saw the idea that if I vary the A12, then the phase diagram changes, and I can go from vapor-liquid equilibria to liquid-liquid equilibria by changing the value of A12, which characterizes how much the molecules like each other or don't dislike each other. So the last thing I wanted to show you anyway was where does this MAB model come from to estimate whether they're going to like each other or whether they're not going to like each other. And so to address that, we can create a very, very simple tinker toy model of how these molecules are interacting. And we can break that down into the acidity. So if you remember the protons on the water, okay, those were blue, right? And so protons are acidic. So the blue parts are the acids. The red parts are the electron density areas. Those tend to be those bases, so they're attracting protons to them. So I've colored the bases red and the acids blue. And you can see then if I had water here, then the base sites would be getting together with the acid sites, and I could form a chain like this of hydrogen bonds. That's essentially what's happening in water to explain the hydrophobic effect. All right, so what's happening when you try to squeeze something like that octane molecule, you remember the octane was all green? When you try to squeeze octane into the water water molecules are all kind of like holding hands. You can imagine a kid's, in the United States, we have a kids game that we call Red Rover, send Johnny right over. So all the kids are holding hands, and Johnny runs very fast so that he can break through the line. And if he doesn't break through the line, all the kids kind of like, they hold hands hard enough that they can throw Johnny back. Then Johnny has to join the line. And then if Johnny is strong enough and he picks the weakest kids, then he can break through the line. You can see it's a mean game. All right. And then this kid's game. So Johnny can break through, and then he can be in the winner's circle. All right. So that's the way we play that game. And so you can see that octane is being Johnny, and he's not going to fit in with any of these things. He can't hold hands even if he does lose. So poor Johnny, he's not going to be able to join this hydrogen bonding network. And all the kids are going to refuse to hold hands with him. They're going to squeeze him out. And that's the way water molecules are. They're just brutal. That's the way kids are too sometimes. Okay, so the water molecules are going to hold hands. They don't want to interact with any molecule that doesn't want to hold hands with them. And so they're going to squeeze the oil out of the water. All right. Well, what about a different kind of mixture? What if you had hydrogen bonding? A lot of times people say, oh, the reason for the solution non-ideality is the hydrogen bonding. Well, but what if you had boys and girls? Boys and girls have hands. So boys and girls can play this game together. It doesn't matter. And so, yeah, you could have boys and girls hold hands like methanol and ethanol, and they'll be perfectly happy together. They'll form an ideal solution. There's not a problem. It's not about the hydrogen bonding. It's about the inability to hold hands. That's what generates the hydrophobic effect. And we might want to actually call it the oleophobic effect, because I kind of think it's more like the water is afraid of the oil than that the oil is afraid of the water. But the bottom line is they don't get along, okay? Because poor little Johnny, he doesn't have any hands, and so he can't join and play with the other children. All right, so he's going to get squeezed out. And a very, very simple way that we can model that is take a look at the acidity of component 1 and component 2. Take the difference of that. Take the basicity of component 2 and component 1. Take that difference, multiply it by this volume ratio, and we get a dimensionless number because these alphas and betas are in terms of energy density. Actually, it's the square root of energy density. So the more energy dense the molecules are, and we mix them at a constant volume, well, the more dense they are, the more energy we're going to have. And for good or ill, right? So if these things are very low energy density, then we won't get any energy no matter what they do, whether they like each other or not. But if they've got a lot of acidity, a lot of acid energy, okay, and a lot of density of that, then we can get a strong interaction energy. And so I've tabulated some acidities and basicities for a lot of molecules in that spreadsheet that I showed you. And so you might not have seen those columns. I think I can show you the columns, even though the solver crashed. Oh, maybe not. Oh, okay, it came back. Let's just stop it. Maybe that's gonna work. I don't know. Let's see if we can find it. Hooray! Actually, I think it worked. Somehow the newer versions of Excel are never as good as the older versions. I don't know who's doing the work over there, but they're not doing a very good job. So this is what the TXY diagram looks like for methanol and water. And so you can see it's not exactly a straight line. And that's because the relationship for the vapor pressure was that sum of Xi gamma I pi sat. But the relationship for the temperature is a little more complicated than that. But hooray, we've solved for the phase diagram, the TXY diagram of methanol and water. Here, let me see if I can move this out of the way. Here are the alphas and the betas that I've used to calculate these MAB predictions. And you can see that this formula is just the exact same formula that I showed you on the screen before. So let's go back. And you can see we could have a lot of questions where I ask you to calculate the interaction for chloroform and acetone. So you just look up, here's, oh, I think I left acetone off the list. Oh, there it is. Okay. Chloroform and acetone. All right. So what we see is that chloroform has a big acidity. So we put that in here. But but acetone has 0 for its acidity. So we have chloroform plus acetone. So acetone is component 2. So we have 0 minus 5.8 for the acidity of chloroform plus acetone. For the basicity, we have component 2 is acetone, 11 minus 0. So this is going to be positive 11 minus 0. So this is going to be positive 11. This is going to be negative 5.8. The volumes have to be positive. So you see that this A12 number, that's going to be a negative number for acetone and chloroform. A negative A12, is that they like each other or they don't like each other? Do you remember that one? The smiley face, that's the one where they like each other. All right. So we can make estimates then of all of our solution non-idealities with this very simple rule, plug it in, get the activity coefficients for the A12 through our excess energies. If the A12 is greater than 2, then we know that the molecules are going to hate each other so much that they're going to form liquid-liquid equilibria, and then we're going to have those more complex phase diagrams like the one at 0.1 bars that we started off talking about. And I think that's a long enough lecture, and I should stop. I think it's been probably longer than a lot of people could tolerate already. So let me leave it there and see if there's any questions that you might have.
Elliott, thank you very much. I think it was lovely, the class. And we can open for 1 or 2 questions because we are at noon already. It's supposed to stop at noon, but I'd like to open for questions. That's a very nice lecture. It's more than a lecture, it's a class. Huh? I have one question. How you calculate this basicity or acidity? Is from Cosmo or?
Well, okay, yes. The original theory for this is called Moss-Sked.
No, I know.
And you can read about it. It won't be in Smith and Maness though. But I'll tell you what Moss-Sked stands for. If I can remember. I know what SKED stands for. So SKED stands for separation of cohesive energy density. So you remember how I was talking about the joules per centimeter cubed, the energy density? So we could talk about energy density in different contexts. So if you were talking about trinitrotoluene, in other words, TNT, that's a very explosive compound that has a lot of energy density, but that's not the energy density that I'm talking about here. So we're not talking about explosive energy density, we're talking about cohesive energy density. So this is that square well energy of attraction. Just how strongly are they sticking to each other? The name for that kind of energy is called the cohesive energy. And so that's what the CE stands for, or actually the CED, cohesive energy density. So what we're doing with the separation of cohesive energy density is we're taking the solubility parameter, which is the overall energy density, and we're breaking it down into its acidity component, its basicity component, and then its overall dispersion energy component. And so that's what these various cohesive energy densities stand for. And MO just stands for modified separation of cohesive energy density. And I don't even remember what the original authors had in mind as the original unmodified separation of cohesive energy density. But that's what MOS.
Well, that's kind of similar from Hildebrand, not
Yes.
Hildebrand, Hansen parameter.
Well, it starts with the Scatcherd-Hildebrand theory, and then Hansen has a way of breaking down and doing the separation of cohesive energy density. So we could call his method the Hansen-Sked, right? His one interesting problem with Hansen's method is, if you look at it closely, he does not allow the possibility of activity coefficients being less than 1. It's just not a part of his theory. And that's a very interesting part of the way the molecules can behave to me, the acetone and the chloroform. The idea that some molecules like each other so much that you could have an azeotrope that is maximum boiling as well as minimum boiling. In the Hansen model, you can't even talk about that.
Yes. Mm-hmm. Okay.
So that's what I liked about this Moss-Sked model. But as we talked earlier on, the way that we compute those graphs of the pictures of the energy densities on the surfaces of the molecules, those were actually calculated by Andreas Klomp. And I asked him for permission and I stole his diagrams, okay, or I liberated them, okay? So those pictures that are on the cover of the book, they're actually generated by Andreas Klomp using the Cosmo-RS methodology. So yes, that quantum density functional theory is indeed the way that those graphs were developed. So there must be some connection between these estimates of cohesive energy density, some correlation, and those Cosmo-RS graphs. And so that was the basis of a paper that a undergraduate student actually, named Marshall Gnop and I wrote in 2016. So if you go to like Google Scholar and look up 2016 with Gnop and Elliott, you'll find a paper where we took the collection of these, they're called sigma profiles is what Andreas calls them, Andreas Klomp. But there was a group that used a public source or publicly available density functional solver and generated these sigma profiles for many compounds. So the sigma profile is a way of taking that three-dimensional picture of the distribution of electron density and representing it in a two-dimensional form. So those sigma profiles basically just characterize that three-dimensional colored picture that we've been talking about. And they've been tabulated by a group at Virginia Tech. So those are public now. So we took those sigma profiles and it developed a correlation then between those electron densities from the quantum DFT calculations and these alphas and betas. Now, the reason we did that is because the MOSCED model only has about 120 compounds to it. And so you quickly run out of compounds. And so as soon as you want to do some scoping of behavior, some analysis for some interesting new molecule or a drug, pharmaceutical, well, you're out of luck. And so using this quantum DFT method, we were able to generate these alphas and betas for about 1,500 compounds. And so we've essentially solved that problem of going from 120 compounds to 1,500 compounds. And remember, this is an approximate theory. So these alphas and betas don't have to be super, super great. They just have to have some correspondence to the right direction that the acidities and the basicities go in. And then after you're done with this very crude model, you want to go to the library and see if there's any mixture data to actually find the value of A12 that fits your data the best. And then remember, this Margulies one parameter model is the very simple model. You might need a more sophisticated model. That's why you want to go and read a little beyond the first lesson in the mixture theory.
Question, people.
I have a question, but also I'd like to call this other question that Troner politely left on the chat. But maybe we should tell the students that if they have time, they could go. So we can like talk about these two questions without holding people that have maybe a compromiso.
Commitment. Just another question, a quick one. You might have noticed, Professor Elliott, that we are recording. Do you mind if we do not plan to make it public, but do you mind if we...
I'm happy to make it public, no problem. Yeah, post it on YouTube, no worries.
Because some students have some, English barrier, English barrier, and they, might want to watch it later.
You know, I think YouTube actually has a what do you call it, subtitles?
Yes.
Subtitling feature.
Yes,
so if you want to post it to YouTube, then you can get the subtitles applied automatically.
Yes, we will do that. Thank you.
Okay.
So, Fred, do you think we can just tell the students that they are like released? And
well, if they want to release, that's okay. Because we crossed the time. But if they can stay, that's nice as well. But I think we can ask if Richard can give us a second continue of this class if he wants to.
Another day.
Yeah, another day.
Yeah, I'm happy to come back and talk more at any time.
Okay.
So can I ask two questions now?
Yeah.
So the first one is from Troner. He was asking about the active learning methodologies. So he wrote, "Dear Professor Elliott, have you always used active learning methods? Did you feel that the students' performance improved?"
Oh, okay. So we actually have an article coming out where it's several authors based on a conference that actually where Fred and I first started having a lot of good discussion. It was called the ECIFAS conference. And so a number of us got together from some presentations at that conference, and then we met again at a conference last summer And we're writing a paper about that. And in the process of writing the paper, I've compiled a number of references about this brain science and the science of learning in general. And it's pretty clear. I mean, there have been numerous systematic scientific studies that prove that the active learning is better. But again, there's a standard deviation on that. It's better in the hands of some people than others. Some people are just really good at a lecture presentation where they write on the board. And so the students can learn from that, I guess. So there's variability within that framework. And so each instructor kind of has to find the best methodology that works for them. But on the average, it is true that the active learning model is the one where students learn the best. And so I guess this question was, did I always teach that way? When I first started out, I started teaching the way that I was taught. And I think everybody does that. And the way I was taught, you got to remember, that was ancient. You know, it was back in the Cold War, right? So ancient history. So what I did was I wrote on the board. And then I got, photocopiers had been invented by that time. And it occurred to me that essentially the students were becoming human photocopiers, but we had photocopiers that we didn't need them to be human photocopiers. So why were we having the students be human photocopiers? It seemed obsolete to me. And as soon as I got to that realization, it was a progression. It was something like, well, we shouldn't be wasting time being human photocopiers. We got to do something better. I don't know what better is yet, but we're gonna figure it out. And we're gonna start doing things different. And from that then on, it was always some degree of active learning. And I've tried things. A lot of what we tried this time is called a concept testing method. It's a pretty crude form of concept testing. In the best form of concept testing, you're really putting an abstract question out there, and the students are having to think about it. These were relatively straightforward questions. In a real concept test, you would not expect the correct answer more than 50% of the time. And then what you should do for a more active setting is first you ask the question, you see the distribution, you see that people haven't, maybe they got 50-50 on this very difficult question. And then you say, okay, why don't you talk to each other and reason it out? And what you'll see is just the act of people talking together, not even being given a hint. The distribution will go more like 70 or 80% correct, just by having the students talk to each other and reason out why they thought the way that they did, and the best answers will rise to the top. And that's a powerful, powerful and positive reflection on this concept of democracy, I think, and human nature. Right? I think it's interesting.
Okay, thank you. So would Stroner like to add something about your question? Because I have another one to follow up.
No, it's pretty clear to me. Thank you very much for the clarification.
Okay, so I would like to ask about this slide 13. And you were talking about hydrophobic and oleophobic. I was recalling some thoughts that I had. So in my head, water and oil, they have the hydrophobic effect, because oil have a huge entropy.
I'm having a tough time hearing. I think somebody needs to mute.
Also, when you heat up, the oil will be more soluble in the water. However, a small molecule like methane is not very much soluble in water, but I believe that's because of enthalpic effect, because the methane is small, but it cannot participate in the
Hydrogen bonds.
hydrogen bonds. So the effect of methane not dissolving its water in water is very different from oil not dissolving in water. So I saved for myself that oil is hydrophobic effect, and methane is other thing. Methane, for example, becomes more soluble if you cool down the temperature, right? So it's the opposite effect.
I wonder if Fred, I think Fred's getting some background noise. I wonder if Fred could mute because I'm having a hard time hearing. Okay, that should work. So you're saying the hydrophobic effect for methane?
I was saying that I had for myself that oil has a big size in relation to water, so it's an entropic cause to the non-miscibility, and when you heat up, the oil becomes more miscible. But methane is a small molecule, and it's enthalpic cause for the non-miscibility, and when you cool down, the methane becomes more soluble in water. So I had that water and oil don't mix because of hydrophobic effect. That's entropic. Water and methane don't mix because of some other name that is enthalpic.
Yeah, so there's a couple of things going on here. So methane, well, first and foremost, remember this model is the most trivial model that we can come up with. So this is a very, very simple model. And so we shouldn't try to push it too hard, okay? But there are a couple of things going on with methane that we hinted at with Dr. Tavares' question. And that was, I left off a column here. I think in retrospect, I should have left it here. And that was the overall solubility parameter that is not separated out. And that's the cohesive energy density for methane. And what you would see is the cohesive energy density for methane, not only is it small, it doesn't stick to itself very well. And so its boiling temperature is 111 Kelvin. Water's boiling temperature, even though they're very similar in size, water boiling temperature is 100 degrees Celsius. Those are very different numbers, okay? And so even though they're the same size, their energy densities are very different between water and methane. And methane is a very low energy density molecule, okay? So that's to start with. It just doesn't have any energy density to begin with. And then there's another strange thing that happens for those molecules that have very little energy density. If you plot their, to talk about methane in water, it's a very infinitely dilute concentration of methane in the water. And so the only way to really talk about that methane concentration in water is called Henry's constant. So it's the Henry's constant that's going to characterize the way that the methane interacts with the water. And there's a lot of things that go into that Henry's constant. What you will see is, especially, let's think about hydrogen, which is an even smaller molecule with even weaker energy density. And it's very easy to see with methane that its Henry's constant, even when it's mixed with oil, its Henry's constant is actually going to go reach a maximum and then start to go down, which means that at a constant pressure, you raise the temperature and the concentration of the hydrogen in the oil increases when you raise the temperature. Okay, so that's a natural effect that's going on simply because you're in the Henry's constant regime with a low energy density component, whether you've got an activity coefficient or not. So what the exact value of the Henry's constant is for or the activity coefficient that sort of corresponds to this in the Henry's law regime, especially at anything above 273 Kelvin, where water is, the thing below that is frozen. Okay, so anything like 300 Kelvin or above, the methane is above its critical temperature. And so it cannot form a liquid. So how do we even talk about the activity coefficient of a component that can't form a liquid? It gets very complicated very quickly, all right? But if we could calculate the activity coefficient of a methane in the liquid, then we would see that activity coefficient is 1, yes. They don't like each other, methane and water. And how it changes with temperature is a pretty complicated relationship that for methane, because it's low energy density, involves both the sort of the bare Henry's constant, regardless of what the activity coefficient, and the interplay of that with the way the activity coefficient is changing. So it's pretty complicated. And this model is definitely not going to do a great job of it.
Yeah, this model is oversimplified to get these correct.
Thank you.
So once again, we would like to thank Professor Elliott very much. It's always a pleasure to learn from you. We could spend the whole day here.
But your stomach might start to growl.
But thank you very much, and we will keep in touch to see another day if we can continue the discussion.
Okay, I look forward to that.
Okay, thank you, Professor.
Thank you.
Thing that's interesting. One thing that came to mind was to talk about a more advanced model of these acid-base interactions. And so the way that these hydrogen bonds really occur is more like a chemical reaction. And so the hydrogen bonding can be written as a chemical reaction. And we can formulate a complete theory based on that chemical reaction. And another interesting thing we can do is take the limit of that theory of hydrogen bonding. As you take the limit of the energy of the hydrogen bond goes to infinity, well, that kind of a bond energy corresponds to a covalent bonding energy. So we can develop a theory of polymer thermodynamics for covalently bonded chains like this from the same theory that we developed for hydrogen bonding. And it's kind of interesting to see how that works out. So it's a much more sophisticated theory about the way the hydrogen bonding occurs than this very crude acid-base model.
Sounds like a great idea.
It's for a class or for a seminar? Because we are because we would like to schedule with you the second seminar.
Okay.
We are going to write down for you.
Any topic of interest. I was just throwing this one out as a way of sort of tagging on to the discussion we've had about hydrogen bonding here today.
Okay. Thank you very much.
All right.
We'll keep in touch.
Enjoy your lunch. And, I look forward to seeing you.
Thank you.
Okay, thank you.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.